my name's Jason Jeffers, and I'm going to be introducing the topic of vectors for you, which is one of the early topics in Specialist. I should hope you find it one of the easier topics, but it does have a sting in the tail at the end on proofs. So vectors, well, just think arrows, arrows, and arrows. Did I mention arrows? So vectors are a really useful thing when we need to talk about, when we need to think about both magnitudes and directions. And this crops up in all sorts of places. It's very natural for it to crop up in physics, where you want to talk about not only how fast something is moving, but in what direction. So you're interested in its velocity, or maybe the position of something, or in which direction forces are acting. It crops up in engineering, all sorts of places in engineering, radio waves, even constructions. It also crops up. They also crop up in lots of areas that you wouldn't even think of. For example, even in computing, you can think of images as being vectors, and that's a very useful thing, and that leads on to things like JPEG compression. And even in mathematics, where you expect to find them, they can be used in some funny ways. For example, functions can be thought of as vectors, and that turns out to be really powerful. So we're going to be talking about vectors, and even though they can be used for really sophisticated things, actually the intuition that you'll get just in the next couple of weeks working on vectors is in fact the same intuition that people use when they're using very sophisticated things. And basically what vectors are useful for is translating between geometry and algebra and calculus. And it can be used to go both ways. What you'll mostly see in the next little bit is how to use vectors to turn geometry problems into algebra problems, and you'll see how useful that can be. Let's start by introducing our friend the vector, and one of the first things to get used to it is there are lots of different notations for vectors, and you often use them interchangeably, so that's the first thing you've got to get used to. So a vector is a direction and a magnitude. So for example, we've got 2 points, A and B. So the vector will be an arrow pointing between A and B, which is the distance between those 2 points, and also the direction going from A to B. So you can write this in a number of ways. Often you'll find, say, V with a little bar on the top is one common way that you'll see a vector written. You'll come across, as written in the notes, A to B with an arrow over the top, which says this is a vector going from point A to point B. You'll also see like a bold V, or maybe a V with a hat on it, and maybe with a bar underneath the V. Whenever you see something like that, it usually means a vector, which means it's more than just a number, it's a direction as well. Okay, now the first thing to realize with vectors is that we're drawing an arrow, but the position that the arrow is in doesn't really matter. All that matters is the direction and the magnitude. So for example, if we've got two other points shown in the notes, C and D, and the arrow between those is parallel to the first one between A and B, then they are in fact the same vector. So the vector from C to D is the same as the vector from A to B, and we've just called that V. Another notation to get used to is in components. So in the notes we've chosen 2 points A and B, and they're at the coordinates. A is at 1, 1, and B is at 2, 4. The vector V is a direction between those two. So we can represent that as 1 and 3 in the square brackets, and that's because the difference in x position was 2 minus 1, and the difference in y position is 4 minus 1. One thing to note with a vector is its magnitude, which is described by the vertical bars. So for example, we've got the vertical bars around A and B, and that is the Cartesian distance between the start and the end point. So for our little vector here, which is 1, 3, its magnitude is using Pythagoras, is the square root of 1 squared plus 3 squared, or in other words, the square root of 10. Basic useful thing about vectors is the ability to translate between geometry and algebra, and later on you'll find calculus as well. So one of the basic things you can do with two vectors is add them together. And this uses the head to tail rule. So if we're looking at the two vectors, we've got a vector A and a vector B. To add them together, you simply put the tail of one vector at the head of the other, and then the line that starts at the tail of the first one. So in our picture here, we've got A is our first one, and B is the second one. So the arrow from the very tail of A to the head of B is the vector A plus B. If we're dealing just with components, as we've got a little example here, we've got 5 and 3 is one vector, and we've got 1 and 7 is the other. You can just add the two components. So we add the x component, which is the 5 and 1 is 6, and the y component, 3 and 7 is 10. The other basic thing we can do with a vector is we can multiply them by a scalar, that is, multiply them by a number, and that has the effect of stretching the vector. So we've got an example here. We've got a vector u, and 2u is then just u stretched by a factor of 2, so its direction stays exactly the same, it's just its length is doubled. We can also multiply by negative numbers, and the negative has the effect of flipping the direction. So for example, we can take u and we can multiply by minus 3 to find minus 3u, and that has the effect of flipping the direction into the opposite to u and stretching it by a factor of 3. We can also, it's also very easy to multiply vectors when they're in the component form. So we've got an example here. We've got 3 times the vector, which is 4, 1. In that case, you just multiply each component by the number of 3. So you get 12 for the x component and 3 for the y. And that's always a very convenient way of doing things. Now that you've actually seen addition of vectors and multiplication by scalar, it's now also easy enough to add subtracting vectors, because that's really just adding two vectors where you first multiply the second one by minus 1. And we've got a little picture here. We've got A and B. So first multiply by B minus 1, and then add them together, and the result is then A minus B. Okay, so we've got a simple little example here of adding two vectors and multiplying by scalars. So we've got the vector A, which is 4, 1, and the vector B, which is 2, 3, and they're written in component form. Now you could try and draw those geometrically, and the example is to work out, well, what is 2A minus 3B? Now you could do this geometrically, but it would be a pain in the neck. Doing it algebraically is much easier. We can take 2 by 4, 1, and then minus 3 by 2, 3. Multiply those as scalars first. So the first vector then becomes 8, 2, and the second vector becomes 6, 9. And then you can just subtract those two vectors component-wise. So we get 8 minus 6 is 2, and 2 minus 9 is minus 7. And so that's the end result. So in theory, you could find that out by drawing vectors and then stretching them by a factor of 2 and flipping it and stretching it by a factor of 3 and get that result in the end, but that would be quite complicated, and that's the point of vectors. They can turn quite complicated geometry problems into quite simple algebraic problems. Now, I mentioned before that there are lots of different ways of writing vectors, and just because you haven't seen enough of them, we've got yet another. And in this case, this is using standard vectors. And we can have vectors in 2 and 3 dimensions. We can have vectors in higher dimensions as well, but you won't need to worry about that, thank goodness. So we've got a picture on the x, y, z plane, so 3 dimensions. And in the x direction, there's a little I hat. In the y direction, there's a j hat. And in the z direction, there's a k hat. They are called standard unit vectors. And they're written on the right-hand side. So I is 1, 0, 0. j is 0, 1, 0, and k is 0, 0, 1. And the idea with these is you can write any vector as a linear combination of those three vectors. So, for example, we can take a vector written as a component as a, b, c, and break it up into each of those standard vectors. So the a then goes with the I vector because it's the x component, the b goes with the j vector because it's the y component, and the c goes with the k vector because that's the z component. And so you can write the vector a, b, c as components as a times I hat plus b times j hat plus c times k hat. And sometimes this is a very convenient way of expressing vectors. So as a little example, so we've got a vector 5, 1, 3 in components, so it's got an x component of 5. And we can write that in terms of the standard vectors. So the 5 goes with the I because it's the x. And so we get 5 I hat plus 1 times j hat minus 3 times k hat. And this is often a more convenient way of writing exactly the same thing. Just as a little note, there's a special vector, the vector 0. That's the vector in components which is 0, 0, 0 for the x and the y and the z component. You could in theory write that as 0i plus 0j hat plus 0k hat. Usually we just write it as 0 with a bar.